problem sheet for questions 1 and 2. Use Monte Carlo simulation to estimate the value of the following integral given a confidence interval for your estimate. And both questions ask the same thing for two different integrals. So it would be useful for us to write some generic functions that we can use to answer both questions. So to find the value of the integral using Monte Carlo simulation, we will sample a lot of points, calculate the number of points that lie below a curve and find the proportion, and then we can multiply that proportion by the area we sampled from to get the value of the integral. So the first function that will be useful for us in both these questions will be a function that will sample a lot of points and estimate the proportion that lie below the integral. So I've defined this function to take in 5 arguments. The first argument will be a function. That will be the integrand itself. So that'll be a function of x. The second two arguments, x lower and x upper, they're the lower and upper limits of the definite integrals. Y max is the largest value of y that we will sample for the y coordinate. So those three arguments together define the rectangle that we will be sampling points in. So from x lower 0, x upper 0, to x lower y max, to x upper y max. And then finally, n is the number of points to sample. So here we will keep track of n, which is the number of points under the curve. I'll start off at 0. And then 4, a lot of trials, which is all the points that we will be sampling. We will create an x coordinate. This x coordinate will be sampling a random number between 0 and 1. Then we're going to multiply that by the width of the rectangle. And then we will add to that the lower limit. So now the x coordinate will be a random number between x lower and x upper. We will sample a y coordinate. This will be a random number between 0 and 1. So this will be a random number between 0 and y max. So together xy is a point within that rectangle. We then want to check whether that point lies under the curve or not. And if it does, we will add 1 to our count of number of points under the curve. And finally we will return the proportion of points under the curve, which is the number of points under the curve divided by the number of points sampled. The question also asks us to give a confidence interval for our estimate. From our lecture notes, we can recall that the confidence interval is given by this formula, where 1.96 indicates that this is a 95% confidence interval. If we wanted other values, so for example, for a 90% confidence interval, we could use 1.64. For a 99% confidence interval, we could use 2.58. These values come from the inverse CDF of the normal distribution. And so we can write this in Python. And so this function will take in the estimated proportion, P, the number of samples, N, and also, so remember that this confidence interval gives us the confidence interval for the proportion. We would like the confidence interval for the integral, which is the proportion scaled up by the area that we sampled from. So the lower estimate for our proportion will be our upper estimate for our proportion. And so our confidence interval will become our lower estimate for our proportion scaled up by the sample area, and then our upper estimate for the proportion scaled up by the sample area. So now to answer the first question, we're asking, use these functions to find this integral here, where the integrand is x cubed plus 1, and our upper and lower limits are 3 over 2 and 5 over 2. So let's first define our integrand. Now let's think what our sample area will be. So what is the maximum area that integrand 1 can take over the interval 3 over 2, 5 over 2? Well, x cubed plus 1 is increasing when x is positive, so that would be whatever the value of this is at 5 over 2. So x lower will be equal to 3 over 2, our x upper will be equal to 5 over 2, our y max will be equal to the value of this integrand at 5 over 2. Therefore, the sample area is going to be x upper minus x lower times by y max. We will also have to decide on how many points we want to sample. Let's say we want to sample 1,000. Now let's start using those functions. We need to import the random library in order to use random.random. My estimated proportion will be this. And therefore, the value of the integral will be that estimated proportion times the sample area. I can look at that and I get a value of 9.9085. I could find the confidence interval, which would give me that I am 95% confident that the value of that integral lies between 9.4028 and 10.4141. Now what you will notice is that if we run this again, we will get slightly different values. That is because we are sampling random numbers, so it would be better if, for reproducibility, if we ensured that that didn't happen. Of course, we are still using randomness, but just to make sure that my answers and your answers are all the same, we will set a seed for our random number generator. Now, every time we run this, we will get the same values out. Okay, now for the second question, we can use the same functions again. Now we just need to define what the second integrand is. And in this case, that is the square root of 1 minus x squared. Now consider what our sample area should be. Our limits of integration, the lower limit is -1. Our upper limit is 1. Over that interval, what is the maximum and minimum value that integrand 2 can take? Well, this is always positive, so the minimum value is going to be 0, and the maximum value will be 1. That takes place when x is equal to 0. We can use the same number of points, 1,000, and now we can work out what our sample area is now. So that is going to be, again, x upper minus x lower times y max. Our proportion now is going to be, when we use the function estimate proportion with integrand 2, our new x lower, x upper, y max, and the same value for n. Our integral is going to be our estimated proportion scaled up by the sample area. Okay, again, let's set a random seed of 0, and we will get an estimate for our integral of 1.542. We can find the confidence interval, so we can be 95% confident that the value of the integral lies between 1.4899 and 1.594.